So where we left off with the last slide on diode VI characteristics was that the current and voltage are related by a nonlinear equation. Current is an exponential function of voltage. That creates a problem when analyzing circuits. I've got a nonlinear set of equations to solve. The objective of these slides are to determine a linear circuit approximation for a diode based upon its VI characteristics, and using that linear approximation, find the current through a diode. The circuit we're going to look at is the following. Find the current and the voltage through the following diode. 5-volt source, driving a 200 ohm resistor, driving a diode. One way to solve that is, as we mentioned before, to use the nonlinear model for the diode. The current and voltage are related by an exponential relationship. As voltage increases, current goes up exponentially. As we talked about before, I could solve two equations and two unknowns, which are nonlinear equations. Or, right now, I'd like to come up with a linear approximation for diode. So here's the problem. I've got the current and voltage relationship here. Come up with a linear approximation. The approach goes as follows. First, estimate the operating point for diode. Here, I'm going to guess the operating point is 0.7 volts and 14 milliamps. Next, at that point, take the Taylor series expansion. Taylor series is given any function. I can expand it in terms of its derivatives. Voltage is a function of current. Express that as a constant plus something proportional to current plus something proportional to current squared, current cubed, and so on. Taylor series. And there's models for diodes depending upon how many elements you take in the Taylor series. Let's look at the simplest case. Let's take the Taylor series expansion out to one term. In that case, the voltage is a constant. The constant that I would use would be my Q point, or estimated Q point, 0.7 volts. So there's my model for diode. If the diode is turned on, over here, the voltage drop across the diode is constant. V sub D, which is roughly 0.7 volts for silicon, varies for different materials. 0.3 volts for germanium, 0 volts for ideal. If the diode is turned off, the current is 0, giving me a piecewise linear model. As you can see, the model isn't perfect, but it's simple. This gives me two states, two different model elements for a diode. I've got the off model. If the voltage is less than 0.7 volts, actually, if the voltage across the diode is less than 0.7, that's right, I have no current flow. The way to model no current flow is just an open circuit. If I have enough voltage to turn on the diode, I get the bottom circuit element. The voltage drop across the diode is constant, 0.7 volts. Now let's use that model to find the current and voltage through diode. With that model, I would first look at the circuit and say, is the current positive or not? Do I have at least 0.7 volts to turn on the diode? Well, I've got a 5-volt source trying to push current through the diode. That's more than 0.7 volts, so yes, the diode will be turned on. Now let's replace the diode with this on model. The on model for diode is 0.7 volts. I can now analyze the circuit. The current through the 200 ohm resistor will be 5 volts on one side, 0.7 volts on the other side. Current is 5 volts minus 0.7 volts over 200 ohms. The current will be 21.5 milliamps. And the voltage will, of course, be 0.7 volts. That, of course, is approximate. The actual answer is 0.7219 volts, 21.4 milliamps if you solve the nonlinear equations. As you can see, the approximation model isn't that far off. I can usually use the approximation that the voltage drop for a silicon diode is 0.7 and be reasonably accurate. Next, suppose that's not accurate enough. Can I come up with a better model? That would be the Taylor series taken out to two terms. Essentially, I'm going to wind up with the voltage drop across the diode is going to be a constant plus something related to current. Gives you a linear set of equations. Essentially what I'm doing is taking my Q point, or where my operating point is as a guess, drawing the tangent to it. That's the red line. The slope is RF. And the intersection right here is V sub F. If you take the voltage, the nonlinear VI characteristics for diode, differentiate, what you get is that RF is NVT, which for silicon is 0.052 volts, over I sub D. That's the small signal resistance for a diode. Once I know RF, I can find VF. I know the operating point is 0.7 and 14 milliamps. I know the resistance. In this case, at 14 milliamps, R sub F is 3.7 ohms. I can find V sub F. And I get my nonlinear, or my linearized model for the nonlinear diode. So now with the two-element model, I get the following for diode. If I have less than V sub F, which is 0.64 volts in this case, there's no current flow. I assume the current is 0, and my model for no current flow is just an open circuit. If I have at least 0.63 volts across the diode turns on. The on model for diode is a constant plus something proportional to current, which is a resistor. Now let's use that to analyze the previous circuit. Again, I'd look at the voltage source and say, is 5 volts enough to turn on the diode? I need 0.63 volts to turn it on. Yes, it is. So the diode will be on. I'll now replace the diode with this on model, which is a resistance and a voltage source. I'd replace the diode with this on model, which is 3.7 ohms and 0.648 volts. I can now find the current through the circuit, which will be 5 volts minus 0.648 volts. The voltage pushing the current through the loop divided by the total resistance, 200 ohms plus 3.7 ohms. That gives me 21.36 milliamps. Once I know the current, I can find the voltage. The voltage will be 0.648 volts plus 3.7 ohms times 21.36 milliamps. Gives me V sub D is approximately 0.7274 volts. And this is a little bit off from the actual current and voltage, but again, a little bit closer. Now the reason you'd use these two different models, if I just want to find the operating point, the Q point for a circuit, oftentimes I just use the single term, a 0.7 volt constant for diode. That's usually accurate enough to find out what my current is through the diode. Once I know the current, if I have an AC circuit, I can use the operating point, the current, to find the resistance, the slope at that point. The slope is oftentimes useful when I have a small AC signal on top of it, such as I'm trying to amplify a signal from your iPad. I'd have a DC signal that turns on the diode. On top of that, I'll have a small AC signal. That's the song that you're trying to listen to. That small AC signal produces current flow through the diode. The relationship between voltage and current is the resistance. I need to have a finite resistance, or I need to know what that resistance is. I need to know what that slope is in order to determine how voltage will get converted to current. That's where RF is used.